Yes, thank you very much for the introduction, and hello everybody. I'm Maria Carpen-Amarie, and I'm going to talk to you about concurrent GCs and their effects on the caches and therefore on application performance. So basically we started this work with the mental model that concurrent GCs pollute the cache for the application in managed runtimes. However, in this work, we found out that actually there are two kinds of applications that exist. Applications that actually see an impact, an important impact from a concurrent GC working at the same time as them, and applications that just don't feel anything from this perspective. So basically this talk and this paper wants to answer the following questions. So for the first group of applications, how big an impact is caused by a concurrent GC running alongside the application, and basically how can we split the applications between these two groups, or how many applications are there in each of the two groups, so to speak. So basically this is what I'm going to talk about. I'll go a little bit through our motivation, methodology, and then our investigation that goes through a micro benchmark and more real-world applications. So our motivation is basically pretty simple. Nowadays, everything is multi-core, so we have the application working on multiple threads, which are called mutators, and bringing blocks of memory into the last level cache there. And the GC working concurrently with the application exactly at the same time, doing its stuff, and also bringing its own blocks of memory into the cache. And therefore, for multi-core systems, the last level cache, or LLC, is basically the contention point from this perspective, because it is shared across all cores. So it doesn't matter where the application and the GC run, they both converge on the LLC. And what is more, the GC can have a different set of memory blocks that is bringing into the cache. So there can be some blocks that are common between the application and the GC, so to speak, that both can use. But it can also happen that the application working set, like the most used part of the application, the working set, is basically totally disjoint from the GC's live set. So this can happen. And the GC can bring a lot of stuff into the last level cache and then evict the application's working set out of the cache, in which case the application doesn't have, so to speak, any more space to bring its working set into the cache. So this was, again, our mental model. We thought, okay, concurrent GC application going concurrently, there must be an impact from the GC pollution on the application performance, we thought. But when we try to actually quantify it, we kind of notice that it's not so easy to do, because the GC cannot be turned off. It's concurrent, so it can't really be that easily isolated. And what is more, the application sometimes does some work on behalf of the GC. So then it's even harder to tease them apart. So we came up with this methodology. We chose benchmarks. We chose to evaluate on benchmarks that have iterations. Iterations that we split into two groups. We call iterations with GC any iteration that overlaps at least a little bit with a GC cycle, with a concurrent GC cycle, and iterations without GC, obviously iterations that don't intersect with the garbage collector at all. So we have these two types of iterations, and we quantify the impact on the application performance based on two distributions for this type of iterations. So basically, what we expected to see was this kind of plot, so to speak, where the iterations that have GC are separate and sort of have more impact than iterations that don't have a GC working alongside them. And in order to quantify it with a simple single number, we used this delta mean, which is basically the distance between the two distributions. And we have distributions because obviously the JVM sort of, well, the applications in the JVM have some variance when they're run. So basically you won't have one number for the iterations, you'll have distributions. So that was our methodology. And we first tried it on a micro benchmark because we wanted a controlled environment there, something that gives us a little bit of determinism, so to speak, because again, in the JVM there are a lot of moving parts. We wanted to be able to do something deterministic and reproducible there. So our benchmark, our micro benchmark is basically a count group by aggregation. But essentially what it is a hash table. It runs, so the micro benchmark runs in multiple iterations. Each iteration is one scan over the hash table in a random order. So that's all it is. And the hash table is basically consists of two arrays, two int arrays. That's all. It's very simple. And in parallel, we have a GC, like not a GC thread, but another thread that triggers explicitly GC cycles whenever we call them. So we call this a controlled environment because we know exactly when the GC is going to work, exactly when we will have iterations with GC and without GC. So it's everything very clear. However, the problem with this micro benchmark was that these int arrays don't really have that many objects. So basically, there's nothing for the GC to do there. So in order to give some work to the GC, we also added a static, huge data structure, which is a directed graph, which we created and just left there to stay. And basically, the GC will have to go over this and mark it in every GC cycle. And it will be, as such, this will be the GC's live set. This and the header of the two int arrays. However, the application's working set in this case is just the hash table because the application scans the hash table in every iteration. So as you can see, in this case, the GC live set and the application working set only intersect over a couple of objects, while the live set of the GC is quite huge. Another important thing is we made the hash table by design fully LLC resident. So it's always, it's almost the size of the LLC, so any tiny thing that can pollute the cache, it will affect the hash table. And the results in this presentation use ZGC as the concurrent GC. We also tested on Shenandoah. For this, I refer you to the paper. And now the results are pretty straightforward. Let me walk you through them a bit. So basically, for this experiment, we run 11 JVM runs, and each time 100 iterations of the micro benchmark. We remove the first, we basically discard the results in the first 15 iterations because we need the JVM, well, in order for the JVM to stabilize and have stable results and so on. And we measure LLC misses and execution time per iteration for the micro benchmark. Now, what you can see here is that, again, we split the iterations between iterations with GC and iteration without GC. The bubbles that you see in the graph are basically per iteration. So it's pretty obvious that always the GC has an impact both on the execution time and on the LLC misses. And it's not any impact, so it's 3x in execution time and 3 orders of magnitude in LLC misses up to that every single time. So it's a major impact and it's consistent across runs and across iterations. And again, it always happens at the same time. So there must be a correlation with this. So basically with this, we were pretty happy with our results. They sort of followed, they sort of fit our mental model there. So we went on to see on more real-world applications. So for this, we chose Renaissance. There are a lot of applications. They come from many classes of software. That's good. They're iteration-based. That's even better for our experiments. And it's important to know that we disabled the GC in between iterations in Renaissance, because if we left it there, then there won't be iterations with GC and without GC. Some interesting observations that we made: some benchmarks had either too few or too many GC iterations after running this experiment. So these are a bit, let's say, can be taken with a grain of salt there, because there are not enough samples in the distributions. But the most important result is the fact that only 5 out of the 23 benchmarks actually show a correlation between GC, the cache pollution produced by the GC, and application performance. These are them. So these 5 iterations show some correlation between this. And please remember, we were looking for this kind of distributions and separation there. However, we don't really see it that much in the results. There's much more overlap than we expected. Also, in this, up here we show the execution time. Down here we show the LLC misses again. However, with this, you can't really see the correlation either too well. So for this, we have these graphs where we actually show LLC misses and execution time together. And you can clearly see how clusters basically form, for example, for PageRank, very well-defined clusters form, are like separate for the 2 types of iterations. However, the results weren't spectacular. The highest performance overhead we got was 10%. The highest impact on LLC misses was 56%. Remember those 3x and 3 orders of magnitude from earlier? Well, they're not there anymore. So what gives? Well, going back to our initial drawing here, basically it's very simple. The equivalent, the real-world equivalent of this drawing is this. Basically what we did is this experiment where we vary the cache size, and we measure the application performance for various cache sizes. And we see that here, the orange lines here basically are sort of flat. That means that if you give them the whole cache or you give them like a tiny piece of the cache, it just doesn't make any difference. So basically, if you run a GC alongside them, it still won't make any difference. So basically, our conclusion here was that this is a unicorn. This doesn't happen that often. And finally, the takeaway here is that, yes, concurrent GC does pollute the cache could have a big impact on the application if the applications themselves were cache sensitive, which they're not. That's it. Thank you very much for your attention. Are there any questions?
Small curiosity, how did you vary the cache size and get that
yeah.
people can graph?
Yeah, so basically there is a technology called Intel CAT. Yes, yeah. Yeah, so basically with that one you can sort of adjust the cache size, so to speak, and the ways that are being used. And
so
yeah.
Changing the cache size was a proxy for garbage collector using that amount of cache?
Yes.
Right.
It's like I mean, you could imagine you would run a core runner, so to speak, with your application and see how much it affects.
Yeah. Right.
Yeah.
Cool.
I have a quick question. What was the, I don't know if I missed it, what was like the RSS that you were generally looking at for the set size for the benchmarks?
Yeah, sorry, what do you mean by that?
Not like the working set, but like the resident sets, like how much memory?
Right. Yeah, that's actually a very good question. So you mean for the Renaissance benchmarks or the micro benchmark? Yeah, so the Renaissance benchmarks we ran with their default configuration and all that. So what I can tell you is that the working set varies a lot between the applications. So some of them had a bigger working set, some of them not so big. And the live set of the GC obviously also varied between applications, but the point is it wasn't so big, so to speak, right? So for example, in the micro benchmark scenario, we had a live set of 5 gigabytes, or rather it was about 60%, if I remember correctly, 60% of the heap size, only the live set. So that was pretty huge. But for example, for the Renaissance benchmarks, the live set wouldn't go over a few percent of the heap size. So indeed, in the Renaissance benchmarks, the GC didn't have that much work to do. So that could also be a reason why we don't see so big an impact there. That's true. But on the other hand, that's pretty much how these applications are run, or officially. So yeah, that's what it is. Yeah. Yes?
Quick analysis. Did you look at the TLB pressure?
Yes, we also looked briefly at the TLB pressure. So basically, yeah, this also had an impact, that's true. In the micro benchmark scenario, basically we used large pages or huge pages so that we reduce this pressure. But yeah, I don't have right now any particular results on that.
Last question.
Yes.
Thanks so much for this talk. We enjoyed the analysis. So I'm interested in this left part of the curve, where you're hitting a particular limit where the workloads do start to experience these
Right.
bottlenecks. Are those connected to the degree to which the benchmark is tuned to the size of the LSC? And would that suggest that if you actually very heavily tune the workload to the LSC, it also becomes more sensitive to GC?
So what we basically thought about this, how we explain this stuff, is that probably in some of the benchmarks, so it's not all of them, I mean, some of them are completely flat, right? But these ones, We believe that some of the benchmarks had some sort of internal data structures, like, let's say, secondary working sets, if you will, like more internal working sets that get, eventually those get hit when the cache is reduced. So, yeah, I mean, eventually there is a performance drop there, yes. But I don't think that's the whole, let's say, the whole working set of the benchmark. It's something like a tiny piece that eventually doesn't fit anymore. Okay, I'm gonna, yes. Thank you.